In this video, we will show that if the matrix A is symmetric, then in the kind of product that we considered in the last video, it doesn't matter whether x is on the left and y is on the right, or whether the vectors are switched and y is on the left and x is on the right. Now, the requirement that the matrix A is symmetric is essential. This identity simply won't hold for all x and y unless the matrix A is symmetric. Now, if you think back to the example with specific numbers in the last video, where we had a 2 here instead of a 3, and so the middle matrix wasn't symmetric, the answer was 11. But now you should go back to that example and switch the two vectors, recalculate the product, and you will see that the result is no longer 11, it is now 4. So unless the middle matrix is symmetric, you cannot switch the two vectors. But if it is symmetric, then you can, and that's what we're going to show in this video. Now later on, when we use this kind of expression all the time in applications, you will find that the middle matrix typically is symmetric, so all is good and the order doesn't matter. Now we're going to show it in two ways. In the first way, we'll deal with the actual entries, and we'll discuss what the answer looks like in terms of the entries of these matrices. In the second approach, we'll use matrix algebra. So it'll be much more blockwise and also much more concise. So let's start with the entry by entry approach, and we've already discussed what the answer looks like. The answer is a single number that's the sum of as many terms as there are entries in this matrix. So that's why I have 4 terms here. And each term corresponds to an entry in the matrix. And that entry pulls out one entry of x and one entry from y. And it pulls out the entry from x that corresponds to its, row, and the entry from y that corresponds to its column. So if you look at this 3, it's in row 2, column 1. So it will multiply x2, y1. So here it is. And let's say this 4, because it is in row 2 and column 2, will extract x2 and y2. So here's that term. And there are 2 more terms in that sum. Now, what happens when you switch the vectors? Well, switching the vectors is in a sense renaming all the y's into x's and all the x's into y's. In other words, we can obtain what the answer will look like, or actually the answer itself, simply by replacing every x with a y and every y with an x. And the question is, will the resulting expression be the same? Very interesting question. Let's see what happens, term by term. Well, this term will certainly remain the same because it's x1, y1. So when you replace x with a y and y with an x, it becomes y1, x1, the exact same thing. So here we were bailed out by the fact that the two indices are the same. So when we switch x's and y's, this term will remain the same. So let me put a check mark here. Another term, which one is the other term in the sum that will have the same property, so we don't have to worry about it? Well, it's this one, of course. Because both indices equal 2, when you switch x and y, you'll obtain the exact same term, and so it will once again be 4x2, y2. It will appear as 4y2, x2, but of course it's the same thing because ordinary numbers commute. These terms are called the diagonal terms because clearly they correspond to the diagonal entries in the matrix. And you would see it even more vividly if we considered a 3 by 3 or any larger matrix. But I think it's still pretty clear now. Now the terms that we have to worry about are these two. In the larger case, there are actually more terms to worry about than the diagonal terms. But here there are 2 diagonal terms and 2 off-diagonal terms. In a 3 by 3 matrix, you would have 3 diagonal terms and 6 off-diagonal terms. These are the terms to worry about. Why? Because if you switch x and y in this term, it becomes x2, y1. So not the same term. And here, when you switch x and y, it becomes y2, x1. So once again, not the same term. Right? But the nice thing is that they become each other, so they switch. They switch. So if the matrix is not symmetric, If one of these is a 3 and the other one is a 2, you simply get a new expression, and that's exactly what you would see if you tried that numerical example with the vector switch. But we're bailed out by the fact that these two coefficients that multiply these terms that trade places are actually the same. And why are they the same? Because the matrix is assumed symmetric. So I cannot put an individual check mark next to each one of these terms, but as a sum, in the combined sense, these two terms are okay. And they're only okay because these two numbers match, and these two numbers match because the matrix is symmetric. And so we have shown in the term-by-term sense, by a term-by-term approach, that if the middle matrix is symmetric, then the order doesn't matter. Now let me show you the proof that based on matrix algebra. It is a very neat and insightful proof, and it is very important to master the ideas that this proof is based on. Consider the product on the left-hand side of this identity. Well, actually, let's pretend that we haven't established this identity and that we have to establish it. This product is a 1-by-1 matrix, and any 1-by-1 matrix equals its transpose. I'm not even using the fact that A is symmetric yet, or anything about this triple product. All I'm saying is that any 1-by-1 matrix equals its transpose. Doesn't seem very helpful so far, but it will prove crucial. So if I were to take the transpose of this matrix, I will end up with the same value. This is not based on anything other than the fact that the result is a 1-by-1 matrix. So this product, transpose, equals, well, we know how to deal with the transpose of a product. It's the product of the individual transposes in the opposite order. And so we have Y transpose, A transpose, X transpose transpose, which is simply X. This is true for any three matrices, X, A, and Y. Now we're going to use the fact that A is symmetric. In other words, it equals its transpose. So this product now equals Y transpose A X. And lo and behold, we got our value on the right-hand side. So this identity is established. So this is much more concise and much more powerful from the algebraic point of view, and can extend to even more complicated products as long as the result is a single number. So we have now established in two different insightful ways that when the matrix A is symmetric, the order of the two vectors in a triple product like this doesn't matter.